So in the morning, we were discussing about this. So we are continuing with Weiss theory, and what we observed is that you have a molecular field of this order, and then we wanted to see how the magnetization changes as a function of field as well as a function of temperature. And then there you saw that this is your M by M naught, and this is A. So depending on the temperature, so this is, let's say, D1, this is D2, this is D3, and this is your magnetization curve. So depending on the temperature, so you will have a certain magnetization at this point, a polarization, spontaneous polarization. Or if you increase the temperature, so at certain point, this magnetization will vanish, and that temperature where so if you take the tangent of the slope of this magnetization curve at the origin, so that slope will be will tell you what is your TC, what is your QE temperature. So this is so again there are many kinds of ferromagnetic materials. So it could be like, so the example, like most used ones, ferromagnets are iron, cobalt, and nickel. So these are ferromagnetic materials. So you can also combine these iron, cobalt, or iron or cobalt with some other paramagnetic material, and that will also give rise to, you can form ferromagnetic material. Okay, so you can take alloys, like we take an example of copper nickel alloy before, right? So in the previous class we had an example of copper and nickel alloy. So you can similarly take this iron with any other paramagnetic material. So you can also have you also get a ferromagnetic alloy. So in that case, so it is always in alloys. So one thing is, so when you look at the, let's say you want to measure the saturation of the specific magnetization, the sigma. So let's say you take so certain weight percent of sigma iron, and then let's say certain weight percent of sigma your paramagnet, or any material for that. So it could be a paramagnet, it could be also a ferromagnet. So that doesn't matter. So if you take an alloy and you want to calculate, or you want to know what is the specific magnetization, so this is your W1 is your weight fraction of component A. So we can write it in a more general way. So let's do that, so and then no confusion. So this is of sigma alloy. The specific magnetization will be equal to weight fraction of 1 and sigma 1 plus weight fraction of the material 1. So weight fraction, so W1 is weight fraction of material 1. So W2 will be weight fraction of material 2, and then sigma 1 are corresponding specific magnetization. Okay, so you can also write W2 will be equal to actually 1 minus W1. So if you have two components, so in the alloy, So you can write W2 is equal to 1 minus W1 as well. And then you can calculate. So if you know what is sigma 1 and what is sigma 2, so you can actually calculate what will be the specific magnetization of the alloy. So here, let's say you can take, so this sigma 1, so this one material can be, so sigma 1, you can write it could be iron, and sigma 2, it could be cobalt. So this will be an iron cobalt alloy. So then, if you know what is the weight fraction, so then you can calculate what will be the specific magnetization of the alloy. So these parameters are known. So similarly, this sigma 2 can also be a paramagnet. So that can be also a paramagnetic material. So maybe it could be sigma like palladium or platinum. So that will also like iron palladium or iron platinum. So that kind of alloy also you can iron palladium. So iron cobalt. So these are some examples. And then, so if you know what is their specific magnetization of individual material, so you can find what will be the alloy composition. So in that way, so taking different weight fraction, so you can go from a heavily ferromagnetic material to a paramagnetic material, like we saw in the case of copper nickel, right? So you can tune the magnetic properties also the similar way like here. So in some materials also it is like you don't take, so you can take a paramagnetic material. So let me that. So if I take this somehow not looking well. So if you take a paramagnetic material, so it's a paramagnet, and here you can put some impurities of the ferromagnet. So these are impurities which are ferromagnetic. Okay. So one, like you take a gold magnet, gold which is diamagnet, and put some ferromagnetic impurity. So you can actually find out how much impurities are there using using your hysteresis measurement. So if you do a hysteresis measurement, okay, so from that, so let's say you can calculate what is your M magnetization, which is you can calculate EMU per centimeter cube, so volume magnetization. So then you can calculate like what is the impurity, how much impurity you have in this matrix. Okay, because you know if you have 100% iron. So if, let's say 100%, so it has certain, let's say, some value x. Okay. So now I have not 100%, so maybe 5%. So if I have 5% of iron here, so I can also calculate what will be y. So that I can measure from the hysteresis. So this would be x 5, so 5% means it will be x into 0.05. So this value should be this much. So you can in fact say if you can measure y, okay, so in a hysteresis measurement, so if you know y, so you can calculate how much impurity you have, magnetic impurity you have in your sample. Okay. Okay. So So this is about ferromagnet. We will come back to some other points on ferromagnet. So before that, I want to discuss so few other kinds of magnetic materials. Okay. So magnetic materials means they have a long range magnetic order. Okay. So in a simple picture, so normally in many textbooks you will see that a ferromagnet would be represented something like this. So this is, let's say, your magnetic moments or the spins. So ferromagnet means all spins will be aligned in the same direction. That is called as a ferromagnet. So this is all long range magnetic ordering. Okay, so there are certain materials also known as antiferromagnets. Antiferromagnets. Okay, so in these cases, so the magnetic the ordering is different. So if you look at alternate spins, so they will be something like anti-parallel to each other. So in this case, M is equal to 0. Okay, so this is called antiferromagnets. So in nature, there are a lot of materials which show this kind of magnetic configuration. So where the spins, adjacent spins or neighboring spins are anti-parallel to each other. So in a ferromagnet, the spins are all parallel, but in antiferromagnets, they are anti-parallel. So the net magnetic moment will be 0. But that doesn't mean it doesn't have a magnetic ordering. Okay, so there is a long range magnetic order still there. So if you look at the order, so this is one periodicity. So where the alternate spins are parallel. Okay, and this spins. So this is one periodicity, and this is another periodicity. So that means there is a regular ordering of the spins. So how do we know that? So typically when we look at materials, we look at them as crystals. Okay, so crystals means they are regular arrangement of atoms. Okay, so regular arrangement is, and it is a regular arrangement in 3 dimensions. Okay, so it expands in both x, y, z. So one simple crystal would be like a cubic crystal. Okay. So this is one like a simple, so not a simple cubic, just let's call it a cubic structure. So then when you make a crystal, so you just, so each corner, so you have atoms in each corner. Okay. And then you just translate it in x, y, z. So you just put more number of q's in all directions, and then you can make a crystal. Okay. So this is how typically lots of materials are defined by their crystalline structure. So they have a crystalline structure. So we will not go into the details of, there can be many different crystal structures. Okay, so one is a cubic, so another is hexagonal, what I discussed, I think. This is another possibility, a hexagonal structure. So now you can take a hexagon and then just, so again, this atoms will be in the corners, okay, of the hexagon, like this, and maybe sometimes atoms can also be in the center, or can be here, can be here. So in this case also atoms can be present here or here. So these are all possible structures which are so possible in the cubic or in hexagonal. So there are many such other geometries which are possible. And when you repeat, so this is called as a unit cell or a unit structure. So which if you repeat, so you get a crystal. So in 3 dimensions, if you repeat it, so you put hexagon, lot of hexagons next to each other and just extend it in 3 dimensions, so you get a hexagonal crystal. So why I'm telling you this? Because when we talk about this antiferromagnets, so we typically look at what is the structure, how the arrangement of these atoms are. Okay. So if I say this, if I take a cubic-like structure and I say this is antiferromagnet, so how do I represent it? So normally it is not represented just like, so I said the neighboring spins will be antiparallel. So instead of that, normally what happens, the spin configuration will be something like this. So I can say this is, let's say, my magnetic moment. Okay. And okay. So what you see is like one plane. So this plane is all ferromagnetically aligned. So this is all magnetic moment. This is pointing in the same direction. So let's say in this direction. But when you go to the next plane, so this is one plane. This is another plane where the magnetization is pointing in the other direction. Okay. And this kind of structure, that is how the antiferromagnets are formed. Okay. So we'll not really go into the details of how. So there can be many actually different magnetic configuration here. So I just give one example. And what are the materials which are antiferromagnets in nature? So if you take any oxide of this magnetic material, so if I take iron oxide or cobalt oxide or nickel oxide, okay, so these are all antiferromagnets. So they have this kind of structure. So this cobalt, iron oxide, cobalt oxide, and so on. So you have this kind of structure, and then they are all antiferromagnets. So what happens? So let's say if we take iron oxide, so you have iron here. These are the iron atoms. So in one plane they are pointing in one direction. In the other plane they are pointing in the other direction. And that is why the total net magnetization from this unit structure or unit cell will be 0, but there is a periodic arrangement of this which exists in all directions. Okay. So you have to be careful when you take a material. So that's why this corrosion, like corrosion means you basically oxidizing this material. So that is actually leads to post performance of material. So you do not want that your material should corrode. So once that happens, if you want working with some material, ferromagnetic material, and that starts oxidizing, so then it will lose its ferromagnetic property. So it might become antiferromagnet. That means the magnetization will decrease. So which is not good. Okay. So then similarly there is another kind of material which is known as they are known as ferrimagnet. Okay, so this is another kind of material, so ferrimagnet. So what is ferrimagnet? So the presentation, like in a simple way, so you can say like this. So it looks similar to an antiferromagnet in terms of that arrangement is alternate spins are antiparallel to each other, but the magnitude is larger for one and the magnitude is less for the other spin. So in that case, M is not equal to 0. Although it looks like antiferromagnet, but the magnetization is not 0. So these are called ferrimagnets. And these ferrimagnets actually, you will see in industries, a lot of ferrimagnets have a lot of applications because they are actually like ceramics. So we will talk about some ferrimagnets. So again, the structure will be something like this. So it is related to this structure, crystal structure. But we will not go into the detail. You can. So we will talk about some of the ferrimagnets. So most common example you will hear are ferrites. Okay. So ferrites, they are known as ferrimagnet. So they are not ferromagnet, they are ferrimagnet. Magnetization is not zero, but this is the kind of ordering you have in ferrimagnets. And they are very useful for your transformer cores, or even certain structure can be used for permanent magnets. So all different applications these ferrimagnets have. Okay, so we will probably talk a little bit about that.